Hey everybody, welcome. We're in section 9.6 now, and what we're going to be doing is one of the coolest things that you can do in calculus. We're going to be finding what are called volumes of revolutions. And a volume of revolution is this. It's when you take some function, such as what I have right here, the y equals f of x, and you rotate it around the x-axis or the y-axis or some line. It doesn't even have to be the x or y-axis. And in rotating it or revolving it around that axis, you end up making a three-dimensional figure. Alright, and what you can do using definite integration is you can find out what the volume of that 3D figure is that you created. And it allows you to find volumes of things that are a lot cooler than just cones or pyramids or spheres or the types of things that you usually find in geometry. You can find volumes of irregular shapes like Coke bottles and that kind of thing. Anyway, let me kind of illustrate what I'm talking about right here. You see the curve f of x, and what I've done is I've just drawn this random curve f of x from when x is equal to a to when x is equal to b. And now I'm going to rotate it around the x-axis. Alright, so watch this. I'm going to rotate the right side around the x-axis. You have to think three-dimensionally here. My artistry isn't always great, huh? And then I'm going to rotate the left side around the x-axis. And then let me kind of finish reflecting this figure in the x-axis. Alright, does that kind of look like a trophy to you or a cup of some kind, hopefully? Again, use your imagination on my artistry there. And what we're going to be able to do is find the volume of that solid figure that we just created. Okay. Now here's kind of the way that that's going to work. Imagine, if you will, that I could create an infinite number of disks, just like taking any point on the curve of f of x and rotating it around the x-axis. Alright? If I could add up the areas, and I did mean areas, if I could add up the areas of each of those curves, then I can find out what the volume of this particular solid is. Technically, a volume is just a sum of the areas of the cross-sections of any three-dimensional shape. Okay, let me take those last few circles away here. That's what we're going to do. And what we're using here is called the disk method. And the way the disk method works is that you find the area of each of those circular disks that you can create by revolving each part of the function around the x-axis. Now let me fill that in. I want this to be a solid disk, not just a hollow circle. There we go. There's a disk. And the concept here is that the volume of the solid would equal the sum of the areas of all the disks from when x equals a until x is equal to b. Alright, now, if we're going to find the sum of the areas of all the disks from x equals a to x equals b, we've got to be able to find the area of each disk. And this is using something that you know very well. To find the area of a disk or a circle, you use pi times the radius squared, don't you? Alright, so we're going to use pi times the radius squared. Now, here's where we need to involve our function a little bit. When we're looking at each of the disks going all the way from left to right, they're going to be different sizes, aren't they? And so, how do we calculate what the radius of each of those disks is going to be? Well, the radius of each of those disks happens to correspond with the value of the function at a given value of x. For instance, this radius right here that I just highlighted, that's equal to whatever the function equals when you plug in b. Same kind of thing at the far left. If I want to know what that radius is equal to, then all I have to do is plug in a into the function. Okay, and I could find out what the radius is right here. Oops, I drew a little too much of that. What the radius is if I plug in 0 into the function. Alright, so my point being that the radius of this disk corresponds with the value of the function at whatever value of x you happen to be examining. Which means that we can say the area of each one of these disks is equal to pi times f of x squared. Alright, and then the volume. Whenever we're integrating, I don't know if you've thought of this too much or not, but whenever we're integrating, that integral symbol is another way of saying that you're finding a sum. You're just adding up a bunch of things. So when we're trying to find the sum of all the disks from x equals a to x equals b, that's another way of saying that we're trying to find the integral from a to b of the areas of each one of those disks. And the areas of each of those disks individually you find by doing pi times f of x squared with respect to x. Okay, or often you can just write that as the integral from a to b of pi times y squared with respect to x. Alright, that formula is how you find the volume of a solid that is created by revolving a function around the x-axis. Alright, now let's see an example. Here we're going to use a definite integral to find the volume of the region bounded by the given curves, or when the region bounded by the given curves is rotated 360 degrees about the x-axis. And you see I've given you several different curves or boundaries for this function. We're going to look at the region bounded by the square root of x plus 3, the x-axis, x equals negative 3, and x equals 1. Alright, let me label a few things here. Alright, what's in yellow there is the graph of the square root of x plus 3, and then I labeled where x equals negative 3 and x equals 1 are, and I'm going to kind of highlight the boundaries then. There's the curve, square root of x plus 3. There's the boundary x equals 1. There's the x-axis. If we needed to, we would draw the vertical line x equals negative 3. We're trying to find the volume of the figure created by rotating that region around the x-axis. And so let me draw the revolution. This drawing part isn't actually part of the process. It's just a good visual for you while I'm explaining it to you. So we revolve that around the x-axis. And let me kind of draw the rest of it. Can you see I kind of have a bell shape right there? It's not quite a cone because the side here is not perfectly straight, this side, or that side for that matter, but it is a bell shape nonetheless. And so we're going to find the volume of a bell, not something that you've done before. And we're going to use the formula that we just talked about a moment ago in order to do that. And there is that formula. Alright, so the integral from a to b of pi times f of x squared with respect to x. Now, a and b are of course our lower and upper limits of integration. We're trying to find the volume from when x equals negative 3 to when x equals positive 1 of pi times, and then the function f of x is the square root of x plus 3. Alright, now remember that corresponds with our radius squared dx. Alright, and quite simply, here's how we're going to evaluate that volume. Let me go ahead and pull out pi, just like I would any other constant multiple, whenever I'm trying to find an integral. And then we're going to do pi times the integral of from negative 3 to 1 of, and then when you square the square root of x plus 3, that just becomes x plus 3, doesn't it? dx. Alright, let me clear some space. And then we'll use what we know about finding definite integrals in order to finish this problem up. Alright, let me keep my constant multiple out front. And we're going to get pi, then times, and let's integrate x plus 3. That's of course going to give us 1/2 x squared plus 3x. And we're evaluating that from when x equals negative 3 to x equals 1. So, pi times, and if I plug in 1, I'm going to get 1/2 plus 3. And if I plug in -3, all right, I get 9 times 1/2, 9/2, plus 9. And then I'll trust that you can do the simplification from there. You end up with pi times -20 halves, or in other words, -10 pi. Alright, hopefully you caught my mistake right there. My fault, that should have been -9, not +9. Which changes things. We're not supposed to get a negative volume. This isn't like the area under the curve where that indicates it is above the curve or below the curve. Volume should be positive all the time. Alright, let me fix the math real quick. Alright, so then you end up with pi times 16 halves, or 8 pi, is the volume of that little bell shape that we made. Alright, pretty cool process, right? Alright, now I've got one more example on the video, and I'd like you to see if you can find the volume of the solid that is formed, and then check your answer against mine. Alright, there you go, same directions as before. See what you can do with it. Alright, for the solution, we're finding the volume of the region bounded by the line y equals 3 minus x, the x-axis, the line x equals 3, and the line x equals 1. Alright, and when you spin that around, it ends up being a cone shape. I mentioned that because if you can see what shape it makes, it helps quite a lot with understanding how this thing is actually working. And since this is actually going to make a cone, we can verify your answer with geometry, to tell you the truth. Alright, let me keep on showing the work. Alright, there's your integral from a to b of pi times the radius squared. Alright, the radius being the function 3 minus x in this case. And then what we're going to need to do is go ahead and pull that pi out front and square that binomial. That'll give you this. Alright, then do your integration. And then go ahead and simplify. And there's what you end up with. Good work if you got it right. If not, see if you can follow my work to try to understand what your mistake was, and or ask me about it in class tomorrow. I will see you then. Have a good night.